Hey, this is Leach with Simpson Math, and today we're talking about the normal model. We'll be looking at evaluating the 68, 95, 99.7 rule, also known as the empirical rule, and applying our knowledge from that to answer some questions dealing with the normal model. But before we dive into talking about the normal model, let's talk about continuous random variables. Now, previously we were familiar with discrete random variables. The discrete random variables were they're just these finite countable numbers. And when we were looking at the probability distribution functions, or the PDFs, of those discrete random variables, they were basically a bunch of line segments. And when we were answering probability questions, we were basically finding the height of those line segments. And if we were answering with an interval, we were looking at the sum of those heights of multiple line segments. And we had to pay close attention whether it was like less than or equal to or just less than. But now we're going to be looking at continuous random variables. So these are things that you could think of like someone's IQ, their height, their weight, things like that, where it's not just number of pairs of shoes, but is a more measurable number instead of something that we count. So when it comes to continuous random variables, instead of graphing a bunch of sticks, we graph a continuous curve. And instead of like adding up all the line segments, but it's like we're adding up all the bits. What we're doing is we would then add up the area underneath the curve of this continuous random variable. This curve is the PDF of the continuous random distribution. But instead of D for distribution, just a little technical note is that it's called a density. Just a minor point, but it's the same idea. It's that PDF. The idea, though, behind this density is that the area underneath the curve all adds up to 1. That should make sense because a complete probability model or complete probability distribution all adds up to 1. In our discrete random variables, if we added up all of our possible probabilities, they would add up to 1. So that's the same thing here. All the area underneath the curve adds up to 1. Now, if I was to form a function out of the area underneath the curve, we would call it a CDF, or a cumulative distribution function. So basically we use the PDF for the picture. That's just a little way to remember it. That's not an actual math term because it's really P for probability, but it's P for the picture of the function, but C, think of it as it's the cumulative distribution. All right, here's some probabilities of the PDFs and CDFs that we should keep in mind. So again, this is continuous random variables, so our outcomes are measured, they are not counted. The curve of the PDF is above the x-axis, and so because probabilities are between 0 and 1 inclusive, then the entire area under the curve is going to add up to 1, as I said earlier. When we're finding the probability of our continuous random variables, we're going to be looking for intervals of x values rather than just individual values. So suppose I have an x-axis right here, and this is a uniform distribution. And I want to find the probability from A to B. Now remember, we've talked about the uniform distribution before. It's just where everything is uniform and has the same likelihood of being successful. So I want to find the probability from A to B, so what literally would be the area from A to B. So it's the all the area that is under the curve, that is above the x-axis, and to the right of A, and to the left of B. Now, if it was some other weird shape like this, and I want to find the area from A to B, it would be the same sort of idea. The area under the curve, but above the x-axis, to the right of A, and to the left of B. All right? Now, for our next one, the probability that x takes on any single individual value is 0. So this is we're finding an area. So if I have a graph, there's my x-axis, and I literally just have a dot, what's the area under this curve? Well, this dot actually has no thickness, and so we're not counting this as area. Now with discrete distributions, we would count that as a length, but not area. All right, so for these continuous graphs, we're looking for area. So because we don't worry about the equal to parts, then whether it's a is less than x, which is less than b, or a is less than or equal to x, which is less than or equal to b, those are really the same thing. So to sum up, when it's a continuous random variables, we don't have to worry about whether it's inclusive or exclusive. We're just looking for these intervals. All right, now let's talk about the normal model. The normal model is a specific named continuous distribution. I alluded to the uniform one earlier, and there are several others out there, but this normal distribution is a named continuous distribution. People often refer to it just simply as the bell curve. It looks like a bell. If I was to stick a handle on this, it could be a bell that it could ring out, or could be like the bell of a trumpet or a tuba or some brass instrument like that. It's a bell curve. Many things in nature often fit this. I mentioned the ones I mentioned earlier of continuous random variables would be that. So typically height, weight, IQ of groups of similar groups of individuals. So if I just said the height of humans, that would not be bell-shaped, but the height of like adult men living in Cuba or something like that. That would probably, that more specific grouping of people like that would be more likely to be normal. A normal distribution just has two parameters, just two numbers that we're interested in, the mu and the sigma, so the mean and the standard deviation. If I know the mean and I know the standard deviation, I know everything there is to know about this normal distribution. So I can shorthand name the normal distribution just like you might have done with the binomial distribution, and we would name it like this. We have our random variable x is being modeled by, we're using this n to represent the normal model, mu to be the mean, sigma to be the standard deviation. So within this course, anytime you see a capital N followed by two numbers, the first number is always the mean, and the second number is always the standard deviation within this course. And so let's take a look at the picture of the normal model. It is this bell-shaped curve. Right smack dab in the middle is the mean. So this distribution is not somewhat symmetric, it is absolutely perfectly symmetric. So since this is perfectly symmetric, that means that the median is also smack dab in the middle. The median and the mean equal each other is what that means since it's symmetric. The mean and the median equal each other. But we're going to be caring more about the value, we're going to be calling that value in the middle the mean because it plays well with the standard deviation. The standard deviation of this distribution is in a very specific spot. Now, I mean, we can calculate and find a standard deviation, but it actually has a presence graphically. So if I was to look at the location of the mean, which is smack dab in the middle, and go up this distance, the distance to the point that this graph switches from being what's called concave down like a frown to concave up like a cup. This point right here, we call this the point of inflection. I'll say that again. So it goes from being concave down, thinking of it like a frown, to concave up. So this is concave up right here. It doesn't technically start going back up, but notice how that could be like a bit of a bowl or a cup, switching to being going up. So this point is the point of inflection. If you take pre-cal or calculus later, that will be an important point in your graphs and analysis at that point. But just for us, we just know that that's the point that it switches. And so that distance from the mean line to that point of inflection, that distance is the standard deviation. So that's a helpful tool whenever you're drawing your normal models. You could always just start with drawing the concave down part and then draw two concave up parts or half of a concave up. And that's a pretty decent way to draw a normal model. And we know there's our mean and there's the standard deviation. Now let's go back to our thinking about the PDFs and the CDFs. For a continuous random variable, we find our probabilities as the area underneath a curve. Now, the bummer is that to find the area underneath this curve, which would be our probability, that would require us to know calculus. Well, seeing as that's not a prerequisite for this class, that's a bit of a bummer. But statisticians, in their everyday life, they don't do calculus with the normal model. They have computer programs and computer software to be able to do that. So we're going to do that same thing. So we're going to be using Desmos, Excel, or just a graphing calculator in order to find the area underneath the curves. But that's really going to be next lecture, is the dealing with that technology. Today's lecture is us to be understanding this normal model and applying a rule to help us approximate the values within this normal model called the 689599.7 rule. This section of text just reminds us that the mean and the median equal each other because the distribution is perfectly symmetric. It also tells us that there's an infinite number of normal distributions. If I just bump mean up a little bit, or the standard deviation to be a little bit wider, that's going to affect the size and location of the graph just a little bit. So there's an infinite number of normal distributions, but there is one that is pretty important, and it's what we call the standard normal distribution. That's when our mean is 0 and our standard deviation is 1. So remember, the first number is the mean, the second number is the standard deviation. So when our mean is 0 and standard deviation is 1, that's our standard normal distribution. What's special about that, think about a distribution that we've already talked about that has a mean of 0 and a standard deviation of 1. That's our z-scores. So this is actually a distribution of z-scores. So let's actually put that on our graph. So first, I need to label my x-axis. So we're going to be graphing the standard normal distribution. So that means that smack dab here in the middle is our mean, which is 0. And then recall that the distance from the center to the point of inflection is 1 standard deviation, and our standard deviation is 1. So that I know that if I add 1, that I would end up here at 1. If I add another standard deviation, I'll end up here at 2. Another standard deviation, I'll be up here at 3. So just a note, these are our z-scores. So this is our mean of 0. I go up 1 standard deviation, go up another 1 standard deviation, go up another 1 standard deviation. I end up with 1, 2, and 3 z-scores. Remember, this z-score of 2, this is 2 standard deviations above the mean. All right, well, if this distance is 1, then that means that this distance is also 1, but I'm going in the negative direction. So that means that this is actually going to be a negative 1 right here. And then skip down another 1, negative 2. Skip down another 1, negative 3. So this is a number line of z-scores. So we have this rule over here to the side. I call it it's the 689599.7 rule. Now, you might be thinking those are some really random numbers, and not random, but just not obvious right off the bat to you. But those three numbers we need to memorize: 68, 95, 99.7. What this 68 is, this tells us that if I'm at the mean and I go up 1 standard deviation and I go down 1 standard deviation, that tells me that of all the data values within that up 1 and down 1 standard deviation, that is 68% of the data. So let me actually color code that a little bit better. So I'm going to color it from down 1 standard deviation to up 1 standard deviation, and all the space in between, I'm going to color this teal. So what this is saying is that the area underneath that curve, so when I go up 1 standard deviation and down 1 standard deviation, that is 68%. So 68% of the area, total possible area under that curve, is within -1 to +1. Just over 2/3 of the data is that close to the mean. That's a pretty dense distribution. All right, the second number, this 95, that's if I go up from the mean, go up 2 standard deviations and down 2 standard deviations, that 95% of the data between those two marks are going to be under the curve. So if I go from -2 all the way up to +2, so let me color all this. I'll actually erase this orange overlay in just a second, but all of this. And then up here from 1 to 2. So everything from -2 all the way up to +2, that's 95%. Almost all 19/20th, almost about 95% of the data is within 2 standard deviations of the mean. If I go down 2 or up 2 standard deviations, that's 95% of the data. Everything that I just highlighted in orange is within 2 standard deviations of the mean. Now I'm going to get rid of that middle orange just so it's a little bit prettier. All right, lastly, the 99.7. I bet you can figure out what this one's going to be. That if I go up 3 standard deviations and down 3 standard deviations, notice that's 6 standard deviations wide, up 3, down 3 standard deviations. That's going to be 99.7%. So that means if I go from all this down here from -3 all the way up to -2, and then all of this including this last little bit from 2 all the way up to 3. So everything that I just colored purple is going to be within 3 standard deviations of the mean, or 99.7%. So almost everything, there's a little bitty sliver that's not in there. Almost everything is within 3 standard deviations of the mean. All right, now that's the empirical rule. That is the 68, 95, 99.7 rule. And we can use these 3 numbers to find several other numbers to be able to answer some questions. Now, I'm not a memorizer. That's not one of my strengths. I do good just learning 68, 95, 99.7. And I know if I know those 3 numbers, I can then find all the other numbers. If you're a good memorizer, you can maybe memorize these other numbers. I do better at just knowing how to get them. For example, what is the area above 1? So if I'm at 1 and I go up, that's the area again. So from 1 all the way up here, all the way up to 2, up to 3, and past forever and ever and ever. What is that area? How much is there? Well, this is what I do when I call the middle percent dance. Now, you can't see me doing this, but this is what I think through my head. So I sort of kind of wax on, wax off. I think, well, everything adds up to 100%. And this middle part is 68%. So then if I was to subtract that and think about what's left over in the wings, 100 minus 68 is 32. All right, let me say that again. So everything adds up to 100. This middle is 68%. 100 minus 68 is 32. So I know that together, those 2 wings are 32. Now this distribution is absolutely perfectly symmetric. So that means, what's the area of just this wedge? Well, it would be half of this 32, or 16%. All right? So if I go from 1 standard deviation up, a z-score of 1 or greater, that is 16%. Now let's do the same thing for 2 standard deviations or up. So everything adds up to what? 100%. This is the middle 95%. Subtract that out. And total left in the wings would be, what's 100 minus 95? Just 5%. Half that 5%, and we end up with 2.5%. So that means from 2, I'm just looking at this part, so from 2 up, a z-score of 2 greater is 2.5%. All right, now let's go from 3 and up. So again, middle percent, everything is a 100%. If all of this is 99.7%, what is left in the wings? Just a 0.3%. So it's half that 0.3, and we end up with just 0.15%. Teeny, teeny, tiny. So 0.15%. Now I'm just drawing these arrows just on the upper half because in a second I'm going to put some percents over here that are different. But just to be clear, that if I was to be at -1 and go down, because this graph is perfectly symmetric, that percent is 16%. And notice, what does 16% plus 68 plus 16% equal? It equals 100%. All right, so that means that from -2 down, that's 2.5% as well. Not writing it down, but notice 2.5 plus 95 plus 2.5 is 100%. And I could do the same thing with this from -3 less than, that is 0.15%. Add those three numbers up, notice we get 100. Now, what's the percent that I get from 0 and up? What is that percent? Well, remember, this distribution is perfectly symmetric, and that mean is at the exact same spot as the median, and the median separates the lower 50% from the upper 50%, so this is the upper 50%. So, of course, the lower 50% plus the upper 50% equals 100. All right, I said I was going to put some numbers over here on this side, so let's look at those. Let's find the area between a z-score of -2 and 0. Now, because of symmetry, this is the same thing as finding the area under the curve from 0 to 1. There are a few ways to figure this one out. The easiest one for this is just to notice that this is 68%. And if I half it and just look at this, that would be half of 68%, or 34. So this is 34%. So from -1 to 0, or from 0 to 1, that's 34%. This one requires a bit more thinking. What is the area from -2 to -1? So this wedge, or separately, this wedge from 1 to 2. Now this one, whenever I ask students to try to come up with this on their own, I usually get 2 to 3 different responses. The easiest is just to use these 16 and the 2.5%. So if I take the 16 and the 2.5, notice that all of this area is 16, which includes what I want and some of what I don't want. The 2.5, if I go from 2 up, all of this area, I don't want that. So if I just subtract them, I will be left with this wedge. And remember, because of symmetry, that's the exact same size as the wedge I'm looking for. So what is 16 minus 2.5? That's going to be 13.5%. And then we can do a similar process from -3 to -2, or from 2 to 3. If I take the 2.5 and subtract 0.15, we end up with 2.35%. This is a good thing to keep beside you while you're working on your homework or doing our next notes examples. In our next video, we're going to be looking at 2 examples dealing with this empirical rule. I hope this helped, and I'll see you next time.